Hi everyone, my name is Niloofar Minbashi. I'm a PhD candidate from KTH Royal Institute of Technology of Sweden. In this presentation, I'm going to present a part of our recent results from applying machine learning algorithms for yard departure prediction, a research that I have been carrying out under the supervision of Professor Markus Bohlin. The agenda for this presentation starts with giving you the main motivation for rail freight research in Europe, the problem in the context of Swedish railways, the model framework that we have had in our mind, the case study that we have chosen for our model framework and the data we gathered for it, then the model algorithms and the results we have obtained so far, and finally conclude the presentation with main conclusions and future directions. The most recent motivation for carrying out research on rail freight transportation comes from the European Year of Rail 2021, which was declared officially by the European Commission. Basically, in this year, we want to establish legal frameworks to boost rail freight transportation, which is quite challenging. And one of the main challenges is actually make a better use of the current capacities that we already have in rail freight transportation across European railway networks. When it comes to capacity in rail freight transportation, we think about the functionality of yards. The optimal functionality of yards in terms of receiving arriving trains, rearranging wagons, and dispatching punctual freight trains to the railway network can contribute to increase the modal share of rail freight transportation in land freight transportation. The importance of this problem has been to the extent that the European Commission, through Shift to Rail joint undertaking since 2015, has dedicated a big part of the Shift to Rail to analyze, optimize, and model yard network interactions across European railway networks. The projects that have been different with different scopes and different objectives and have been continuation from each other. The results that I have presenting in this presentation are a part of the work that we are doing on Freight Rail 3 project, which is financed by the Swedish Transport Administration. If I want to give you an overall of the research trends about yard studies, I can start with the first trend of research, which focused on the classification yard. And in this trend of research, we think that the classification yard is the bottleneck in a rail yard. And by improving it, we can have a better performance across the yard. Later on in the second trend of research, the researchers focus on the whole yard as a whole system and try to capture the interrelationships between different subyards and mainly through simulation. And even if this approach is more comprehensive, but still it looks at the yard from a single entity and a separate part of the railway network. The most recent trend of research comes from connecting yards to the network. In this new trend of research, we think that the yards impact the network and vice versa. And if we want to improve the rail freight operations, we need to consider these interactions between yards and networks. Actually, in this research, we want to move towards this trend of research, and we have tried to go towards it. But if I want to describe the specific problem of yards in Sweden, if we want to implement prediction models for yard departures in Sweden, we need to face three main issues. The first issue is, as you can see on the left side, the departures from the yards in Sweden are highly deviated, positively and negatively. The point is that we have the early departing from the yards, which is a common practice in yard practices in Sweden, which wants to compensate for the negative impacts of the runtime delays that might occur. So the yard operator dispatches the freight trains early. This highly deviated deviations makes it difficult to find previous statistical distributions to the whole range of departure deviations. So the problem cannot be solved with classical methods of classical statistical methods. The second issue is that there is a disparity between the departure status. The majority of the departures are early, which if you want to go towards machine learning approaches, that's make the problem imbalanced, and most of the predictions will be predicted as early. The third issue is that yard operations are highly human dependent. And most of the conflicts in the yards are resolved by the yard staff. And some of these conflicts are not registered in the data or are not explicitly captured from the data. From this side, we can say maybe the machine learning can be a good approach towards a yard departure prediction, because maybe by machine learning, we can learn from the historical data we have and try to capture these interrelationships that are not captured explicitly by different or previous methods. With all that said, we have come up with a model framework that tries to predict the departures from the yard in 3 stages. Basically, we use historical data from yard operational data sets and train some machine learning algorithms, then test them to validate the model. And at the first stage, we classify the departure status by early, on time, and late. In the second stage, we predict the actual departure deviations, how early or how delayed the train was, which is what I'm going to present now. And finally, in the third step, we want to use these departure deviations as input to a macroscopic network model that the infrastructure manager has, and to see how the yards may impact the running of other trains, or use this connection between the yard machine learning model and the macroscopic network model to see how the timetable can be evaluated through this connection between a macroscopic model and a machine learning model. For this model framework, we used the case study as Malmö yard, which is the yard in the south of Sweden. And as you can see with the star on the map on the right side, Malmö yard is a strategically important yard for both Swedish railways and the European railways. It is located on the Scandinavian Mediterranean corridor. And if you want to have a higher share of modal share for railway transportation, this yard needs to operate in a more optimal way to connect Scandinavia to the rest of the railway network in Europe. Malmö yard has also an unconventional yard layout, which is a single-ended yard layout, and the arrival and departure yard are the same. This different yard layout makes a little bit handling the yard difficult, and in the recent years, Malmö yard has been identified as the most delayed yard in Swedish railways. The data we gathered for Malmö yard was 1 year of operational data that comprised of 3 data sets: wagon connection, train punctuality, and train features data set. Overall, it comprised of more than 160,000 wagon connections, from which 10% were duplicates, and finally we had more than 144,000 of wagon connections, from which we extracted 30,000 of train connections, which were equivalent of 8,000 departures. We chose to use the train connections because, as we showed last year, the train departures 8,000 is not enough to implement a machine learning approach. So we chose the train connections to have a sufficient amount of data. From this data, we gathered different predictors to predict the target that we have, which is departure deviation. From the wagon connection, we extracted minimum wagon dwell time, maximum wagon dwell time, number of wagons per departing train, and number of arriving trains that contribute to a departing train. Basically, we wanted to capture some operational idea of the parameters. Train punctuality predictors were departing train number, which stands for local, long distance, and foreign trains, scheduled departure hour, weekday, and month. And from the train features, we just needed the maximum operated length and weight. We implemented our model using two algorithms. The first is a decision tree, a single decision tree, which is made up of nodes and branches. Basically, at each node, we use an input feature or a predictor, and like the train weight, if it was more than 1,000 or not. And then the train develops, and finally, we find patterns that led to different departure deviations. A single decision tree is interpretable, it's easy to understand for the infrastructure manager, and has these advantages. Then we use an ensemble version of a decision tree, which is a gradient boosted tree algorithm. And when we move towards ensemble versions, we have different trees that are put in predicting different areas of the data. Then if we choose to use the ensemble of these trees, then we will have on average a better performance compared to a single decision tree. We choose 80% of training data sets and 20% for the testing. The evaluation criteria was the most common evaluation criteria for evaluating the performance of machine learning algorithms. The results we have obtained, the most important thing to show is that so far we have come up with this conclusion that in decision trees, in applying decision trees, the ensemble version as in a single decision tree have a slightly different performance. Maybe the ensemble version is slightly better performance, but overall, a single decision tree can be more interpretable and more practical for being used by the infrastructure manager or the yard operator. Looking at our evaluation criteria, first we chose R-squared. And the R-squared shows the proportion of the variance of the training data sets that was captured by the model that we have. And basically it shows the accuracy of the model. And we see that for the single decision tree, it was 86%, and for the gradient boosted tree, it was 89%. So the model is very good at capturing the variance in the training data set. The second parameter was mean absolute error, which is per minute as the departure deviations, and shows that our predicted values are more than 2.5 minutes, are different from the actual departure deviations in 2.5 minutes. The third parameter was mean squared error, which is actually the average of the squared errors. And the more it's closer to zero, the better the model is, but this is never achievable in predictive models. The other parameter that was important for us was root mean squared error, which is the root of mean squared error. And because it gives more importance to the big deviations, it shows that our predictions are different from the actual departure deviations, around 14 minutes in the simple regression tree and around 12 minutes for the gradient boosted trees. These evaluation criteria give information on the size of the error that we have. If you want to see what was the direction of the error that we had, we need to have the mean signed difference, which shows if the predictions were higher than the actual prediction. And for the simple regression tree, it was 0.7 minutes. That was actually higher than on average on the actual departure deviations. But for the gradient boosted trees, the mean sign difference was 0.08 minutes higher than the actual departure deviations. This shows that our model on average predicts higher than the actual departure deviations. Presenting the results now, we can move on to the conclusion. The main conclusion is that the amount of data matters in this problem. We have simplified by using the train connections instead of just mere train departures. The second main conclusion is that comparing a single tree to an ensemble tree, it's better to use a single decision tree because it's more informative and more understandable from the infrastructure manager. side, and it gives like the real patterns in the data. The future directions are, we can go for comparative analysis of different machine learning algorithms. And also something that I have in mind is that I would like to run this model on data from other yards in Sweden or European railways. And finally, what I've been working on is that we want to connect this yard model that we have now to a macroscopic network model and to evaluate the timetable and so on. I would like to thank you for the opportunity to present at Informs, and I'm ready for any question or any discussion.